Now let us see what is the relationship between the change in potential energy due to a motion of the crack tip and uh, the Jk values. So what we are envisaging is that there is a crack tip here and there's a region around the crack tip which we call V1, within which the effects of this crack tip stress field are uh, are constrained. So the effects outside this region V1 are small, and the crack tip moves from a point A to B, so that the yellow region moves from V1 to V2. It's like a rigid body motion of the region around the crack tip. It's self-similar crack growth. So that means that this stress field, that is high stress field, that is attached to the crack tip actually moves with the crack tip and has more or less the same shape. So what we are going to do now is we are going to calculate the change in potential energy of the body between these two states. This is what we had done in case of the energy release rate as well. We are going to calculate this and connect it to the J integral, the J1, J2, J3 values. So here is how we do it. So d pi, which is the change in the potential energy, is, let's say there are no body forces. So body forces are zero. Therefore, in the second state, in the moved state, when the crack tip has moved by from A to B, this is the potential energy. And when the crack tip was at its original location in A, this was the potential energy. So the difference between them is what uh, we, we call d pi. So this is the strain energy stored and this is the potential of the load. There is no potential due to the body forces because we have neglected body forces. Now we can write this as this and this. We can write as W dV over V2 minus V1, and this and this we can write as two separate integrals, 1 over delta V2 and 1 over delta V1. Okay, now we will calculate these integrals separately. Now let us assume that the crack has moved along a vector d zeta. It's a small motion along d zeta, and as a result, this region of high stresses has moved from V1 to V2, and is, as this is a rigid body motion, the point A prime, which was lying on the boundary of V1, has moved to B prime, which is lying on the boundary of V2, boundary of V2, and this vector is also d zeta because it's a rigid body motion of this yellow region from V1 to V2. And the normal at that point is equal to n. In that case, the displacement at UB prime can be written in terms of UA prime using the Taylor series. So UB prime, the displacement vector at UB prime, is equal to the displacement vector at UA prime plus del U del x at A prime times d zeta. This is just the application of Taylor series. So what we have written is basically UBI is equal to UAI or P prime, A prime I plus del UI del x j at A prime times d zeta j. So this is what we have written here in vector notation. So this is on del V1 A prime. This is on del V1. On the right hand side, so we are trying to get the displacement at B prime in terms of displacements of the corresponding point from which moved to B prime, corresponding point A prime which moved to B prime. So now this expression, this expression will be put back into here. So for this integral over delta V2, we will replace ui at delta V2 in terms of the Taylor series, which is framed now in terms of ui at delta V1 and the derivatives. So we will put this expression into the traction relations. So this is delta, this is the traction relation, work done by the traction on delta V2 minus work done by traction on delta V1, and this Ui on delta V2 is replaced in terms of the Taylor series expression that we had in the previous slide. And if you now assume that the tractions have not changed, why have the tractions not changed? Because the stress field around this crack is exactly the same as the stress field around this crack. The stress field around the crack has not changed. The crack has just moved. So this region, the tractions on the boundary of this region remain exactly the same, because these two eggs, the yellow egg and the dotted egg, are actually the same, just located at different crack tip locations. So the tractions on this boundary have not changed, and therefore this Ti and this Ti are the same. I can take it common. Then this guy cancels with this guy, which is ui on del v1. So this guy cancels. We are left with this derivative, and this is what we have. And Ti can be written using Cauchy relation as sigma ij nj, and this is the result of the first integral, of the second integral, the traction integrals, in terms of a contour integral over delta v1. Okay. Now we will evaluate the first term, and in the process of doing it, we will again assume that this yellow egg and this dotted egg are just rigid body translations of the same domain. Okay, so to calculate this dv, which is the difference between the two, we take a small element of area on del v1, and the height of that is d zeta times d zeta dotted with n. So zeta k nk times ds gives the volume of this small cylinder, which is based on ds. So dv can now be replaced by this. So w dv is replaced by this. And then if you integrate this over del v1, this whole thing, so ds spans over this whole thing, then you will get this extra volume v2 minus v1. So this integral is now over del v1, and dv is replaced by this. Just imagine it, if I now span ds over this whole delta v1 area, I will get the difference in volume between v2 and v1. So that's what I have done. This is w dv integrated over v2 minus v1, and this was the work done by the tractions integrated over delta v1. So I have both evaluated over delta v1. So I can now write del pi as an integral over delta v1 as w d zeta k nk, that is this integral, and then this one, which was the difference between the traction terms. So this integral, both over delta v1, though both integrated over ds. So this is what I get, and d pi is just d zeta k. D zeta k is an arbitrary motion of the crack. So crack tip, arbitrary motion of the crack tip. So d zeta k comes out of the integral, and we are left with this quantity, which you will now recognize as your jk, as we had defined it earlier. So d pi, the change in potential energy due to a motion d zeta of the crack, is given by d zeta dot j. So this is a bit like a work done expression. That's why J is sometimes called the crack driving force, though it is not a force. So this is like a force times a displacement gives you a work done. But in this case, this is the change in potential energy is given by jk times d zeta k, where d zeta k is the motion of the crack. So any self-similar defect, it doesn't have to be a crack tip. If any self-similar defect moves in this manner by a quantity d zeta, so that the region of high stress around this defect moves like a rigid body with it, then this expression will be true. This is called a configurational force because it is the energy change due to a change in configuration of a defect. So this defect moves from here to here, and to do that, this is the energy change that occurs. So uh, this is the explanation of this quantity Jk. This quantity Jk times the motion of the crack tip gives you the total energy change that occurs. And therefore, in this problem where we had calculated J1, this problem where we had calculated J1 to be this, remember, this was the problem that we had, and we had calculated J1 to be P square by 2A, 1 minus EA, 1 minus EB. So the change in energy, if this interface now moves by ds1 in the one direction, then the change in energy of the system d pi would be j1 ds1, and that is written as here. I have taken zeta 1, not s1, zeta 1. So j1 d zeta 1 would give you d pi for that problem. So that's what is given here. So this completes our explanation of what a configurational force is. What is a configurational force? The configurational force arises due to the motion of a defect. It's a self-similar motion of the defect in the sense that the stress field created around the defect moves in a self-similar manner with it. So in the changed position, the surrounding of the defect, the stress field surrounding the defect is exactly the same. So this domain moves like a rigid body. If that is the case, then the change in energy, the change in potential energy of the system is given by Jk d zeta k. That is the significance of this quantity J. So we will stop here, and in the next we will see how this can be applied to a 2D